Hi, in this lecture, I'm going to talk about one of the most fundamental techniques for solving array question. That's called one-pointer technique. I'm going to briefly introduce what is a one-pointer technique and then show you several examples of how to using one-pointer technique to solve these problems. So let's get started. One-pointer technique usually uses one pointer to access elements from an array and several variables to store intermediate states. If we assume that we need to traverse a whole array, it usually takes O(n) time complexity and O(1) space complexity. Let's use the following example to demonstrate it. This example is pretty simple and straightforward. Find the largest element. Given an integer array of size n, find the largest element in it. As we can see from example 1, the elements of this array will be 3, 2, 1, 4, 5, and 5 is the largest element in this array. Here we provide you several constraints, so you don't need to worry too much about whether element within array is too large or too small to fit with the integer, as well as the array size is too big to fit with the integer memory. I suggest you to pause the video here and try to solve it by yourself. And now, if you come up with your solution, let's jump into our solution. Since we haven't been told that this array is sorted, we need to access every element in this array in order to find the largest one. In this case, we can use one pointer called I to access elements in one variable called max to store the current maximum element, as we can see from the following picture. We can move the pointer I from the left to the right of this array and update the max variable on the fly. Once we finish traversing this array, the max is the largest element we want. This solution takes O(n) time complexity because we went through all n elements within this array, and O(1) space complexity because we only create a variable called max. And below, as we can see, is the Java implementation of our solution. Here we create a class called the largest element and create a method within this class called findLargest. And the input of this method will be the original array nums, and the output of this method will be the maximum element within this array that's represented in integer format. At the beginning, we initialize the max equal to -1, and then we create a variable called I to traverse this array using the for loop. And at each step, we update the max to the current maximum number we have seen so far. And finally, we just return the max. That's the largest element we want. Let's walk through this code using example 1. At the beginning, since I at the index of 0 and current maximum number is the first element within this array will be 3. And after that, we move index from 0 to 1, and current element within this array will be 2 smaller than 3, so that we keep max equal to 3, and then we move the I from 1 to 2. Current element will be 1. Since 1 is smaller than 3, we still keep max equal to 3. Then we move the index from 2 to 3. The current element will be 4. And since 4 is greater than 3, we update max from 3 to 4. And finally, we move the index from 3 to 4, and the current element will be 5. Since 5 is greater than 4, so we update max equal to 5. And finally, we just return max equal to 5. Hopefully this solution makes sense to you and similar to your code. And now let's jump into another example. This example is from LeetCode called majority element. Given an array nums of size n, return the majority element. The majority element is the element that appears more than floor of n over 2 times, and you may assume that the majority element always exists in this array. For example, as we can see in example 1, the elements within the array will be 3, 2, 3. Since the appearance time of 3 is 2, that is the greater than floor of 3 over 2, that's 1, so that the majority element in this case will be 3. Similarly, we can get the majority element of the arrays in example 2, it will be 2. Here, we also provide you several constraints for easily processing. This question is a little bit trickier than the previous one. I still suggest you to pause the video here and try to solve it by yourself. And if you have finished this step, let's jump into our solution. This question is a little bit trickier than the previous one. The idea is that we can use one pointer to access every element in this array and one variable called m to store the current majority element. But we need to add another variable called count to store the appearance time of the current majority element, as we can see in the following picture. Then we move our pointer from the left to the right to traverse this array. If we encounter an element that is the same as the current majority element m, we can increase the count by 1. Otherwise, we decrease the count by 1. And now, if the count is smaller than 0, we need to reset the current majority element m to the current element, and also set the count back to 0, as we can see in the following picture for the whole process. And since we know that majority element appears more than floor of n over 2 times, so that we are guaranteed to get the majority element in the end, which count no less than 0. And the above algorithm is actually called the Boyer-Moore majority vote algorithm, which takes O(n) time complexity and O(1) space complexity to find the majority element from an array. And here is the Java implementation of this method. We create a class called majority element and create a function called majority element within this class. The input of this function will be the input array nums, and the output of this method will be the majority element represented in integer format. At the beginning, we initialize the m equals to -1 and count equals to 0. Then we create a pointer to traverse this array using the for loop. At each step, as we mentioned, if the current element is not equal to the current majority element, we just decrease the count by 1. Otherwise, we increase the count by 1. If we notice that the count is smaller than 0 currently, we need to update the majority element m equal to current element num, and then reset the count equal to 0. After we finish traversing this array, we finally get our majority m and just return it. Again, let's walk through this code using example 2. The elements within this array will be 2, 2, 1, 1, 1, 2, 2. At the beginning, our current majority element will be the first element of this array, that will be 2, and the count will be 0. And next, we move to another element that is still 2, so that we increase the count to 1. Then we see a 1, so that 1 is not equal to m. Then we just decrease the count to 0. Then we see another 1. Now, since the 1 is not equal to m, and we need to decrease the count to -1. And now we notice that the count is smaller than 0. We need to reset the m equal to current element 1 and reset the count to 0. And then we move to another 1. Since the 1 is equal to m, that is 1, then we increase the count from 0 to 1. Then we see a 2. Since the 2 is not equal to 1, and then we decrease the count from 1 to 0. But we still keep the majority element m equal to 1. Then we see another 2. And now we decrease the count from 0 to -1. Since the count is smaller than 0, we need to reset the m equal to 2 and the count become to 0. And finally, we return m equal to 2. Hopefully this solution makes sense to you. And if you understand it and find it similar to your code, that's great. Congratulations. But if it's a little bit different, just try to understand it and try to re-implement it by yourself to make sure you fully understand it. In the next lecture, I'm gonna provide you another example to further demonstrate how to apply one-pointer technique to solve more questions. Stay tuned and thanks for your time. See you in the next lecture.